Okay, hello physical science. We're going to continue on today with section 3, and the title of this section is measurement. And it's going to be broken up into at least two parts, if not more, because it is a little bit of a longer section. And this one is important because if you remember from our last section, we talked about using the scientific method and how following those steps were very key to gathering the correct data, to have the correct approach. And while we are doing that, we're obviously going to carry out experiments, so there's going to be numbers and things that we need to record. So that is why we're going to spend a whole section on measurements, because it is a little bit more detailed than what you might think, and in the scientific world we do it a little bit differently than what we do in everyday life, but we will get to that here in a second. But to start, they're just going to give us some examples of measurements that kind of help put it into perspective with your real life here. So it starts by just saying, how old are you and how tall are you? So the answers to these questions are measurements. So whether or not you know it, we are actually having tools to tell us how old and how tall we are, and they're very important in both science and everyday life, and it would be really difficult to imagine doing science without any measurements. So that is, again, it is an integral part of what we're going to do in this class, being able to correctly measure things and to do it accurately in order to ensure that we have the best results possible. And our next section is going to be something called scientific notation. So scientific notation, if you have not heard, is something that's very useful. So I'd make sure at this point I would just jot this down, those two words right there, scientific notation, and we're going to talk about what it is and why we need it. So if we look at why it is useful, and it is because that scientists often work with either very large or very small numbers. And astronomers, for example, estimate that there are over 200 billion stars in our galaxy. Now, if you're an astronomer and you're constantly working with that number, I don't know about you, but I would get tired of writing out all those zeros. So we're going to see here in a second that scientific notation is almost a type of shorthand in order to keep us to kind of not have to waste so much space, and makes it a little bit easier to manage those really large, or kind of on the flip side of that, those very small numbers. So it is a way to get our official definition, so I'd make sure I have this written down. It is a way of expressing a value as the product, so we're going to multiply here, product, some math terms coming up in this chapter, of a number between 1 and 10 and a power of 10. So if that doesn't make sense to you, I think if we look at the example, it really helps. So for our example is, the speed of light is about 300,000 meters per second. So in scientific notation, that speed is 3.0 times 10 to the 8 meters per second. So if we look up here, it's expressing the number. So right here, the 300,000, we have the 3.0, and the product, so that's where we multiply. So that's where the product sign comes in. We always have a multiplication of the number between 1 and 10. So again, right here we have 3 and the power of 10. So it's 10 to the 8th power. So that is how scientific notation works. Again, the definition almost makes it a little more confusing than what it actually is. It's basically just a shorthand for writing out large or small numbers. So the exponent, which again have some math terms coming up in this chapter when we think about measurement, tells you how many places the decimal point needs to move. So it is really 8 places to the right of the 3. So in all reality, this number right here, 3.0 times 10 to the 8 meters per second, is exactly the same as this right here. So again, we can go over some more examples, but hopefully that kind of makes sense to you. Again, shorthand for writing out numbers. And we're trying to go to our next one over here, and we can use it for other ways other than just large numbers. We can use it for small numbers. However, this time, if the number is less than 1, we're going to write our exponent as negative. So for an example, the average snail's pace, again, someone said you're moving slow as a snail, you can actually say, no, I'm not, because you know now that a snail actually only moves at 0.00086 meters per second. So in scientific notation, that speed is 8.6. So again, we have our number between 1 and 10 there, 8.6 times 10 to the negative 4 meters per second. So we would just move our decimal place over to the left. So the negative exponent tells you how many decimal places there are to the left of the 8.6. So that's kind of on the exact opposite of the positive. So positive, we're moving to the right. Negative, we're moving to the left for scientific notation. And now We're not just going to have it so simple as we can just write them out that easy. We can take a big number, condense it down to scientific notation. We actually, the main reason why we can do this is we can actually work with these numbers in a math problem to actually kind of give us some answers to questions that, again, might take up a giant sheet of paper if we didn't have scientific notation, but if we do, it can really condense it down. So to multiply numbers that are written in scientific notation, you multiply the numbers that appear before the multiplication signs and you add the exponent. So that is the big rule here. So we multiply the numbers that appear before the multiplication. So if we look here, we have 3.0 times 10 to the 8th, then we have 5.0 times 10 to the 2. So we multiply the numbers that appear before, so we multiply the 3 and the 5 together, and that is what gives us our 15 right there. And then we do not do the same to the exponents, we only add the exponents. So remember, our exponents are up here, so we have an 8 and a 2, so we have 15 times 10 to the 10, and if you remember, this number has to be between 1 and 10, so we have to move our decimal place over 1, and so because we make it 1.5 instead of 15, that means we need to add an extra exponent up there. So that is how we arrive times 1.5 times 10 to the 11th. And so again, that is actually the distance between the sun and the earth. So the sun and the earth are 1.5 times 10 to the 11 meters apart from one another. So for our last one, we're going to talk about dividing them. So dividing them follows very similar rules. So when dividing numbers written in scientific notation, you divide the numbers that appear before the exponential terms. So again, right here we have 1.5 times 10 to the 11th, 3.0 times 10 to the 8th. So we divide the 1.5 by the 3.0, and that is where it gives us the 0.50 over here. And then we then subtract the exponents. So we have an 11 on top, we have an 8 on the bottom. 11 minus 8 gives us 3, and this again right here, so our final results are 0.5 times 10 to the 3rd. And again, remember that we have to make it a number between 1 and 5, so we move that decimal place over to the right, and so then that gives us 5.0, and instead of now 10 to the 3rd, we have 5.0 times 10 to the 2nd power. So that are the rules. Make sure we don't have any more. Okay, so we have a little bit of an example right here, and you know what? You can maybe work on this example actually on your own, and we will go over the answer together. So remember, this is a multiplication problem, I believe. So it says a rectangular parking lot has a length of 1.0 times 10 to the 3rd meters and a width of 2.4 times 10 to the 3rd meters. So what is the area of the parking lot? So this is going to be our last bit for this video, so you're going to have to figure out what that area is, and then we'll go over the answer together in class. So that is it for this video. Let me know if you have any other questions.